In today's lesson, we are going to talk about infinite series and how to write a repeating decimal as a fraction. Okay, so first of all, what is an infinite series? An infinite series is when we have a sum of values in a sequence which are added up infinitely. Now, there are two different types. There is convergent and divergent. When we have a convergent sum, this is when the sum approaches a value as n gets infinitely large. This is going to happen when each term in a series gets closer and closer to 0. And we will see this when we have a geometric series with the absolute value of r less than 1. So if we were to have a series with r equaling 2/3 or r equaling -1/4, both of those would have an infinite sum that exists. If the r value were to equal 5, for example, then in this case, the infinite sum would not exist, and we would use the acronym DNE. The other type of infinite series we have is what's called divergent. And in a divergent series, this is when the sum gets infinitely large, whether really large in the positive sense or really large in the negative sense, and in this case, it does not exist. This is going to happen when each term gets farther and farther from 0. And this happens with our geometric series when the absolute value of r is greater than 1 and always in our arithmetic series. All right, so how do we go ahead and find the sum of this convergent series? Well, if you recall, we learned the other day that the sum of the n terms in a geometric sequence would be a1 times 1 minus r to the n, all divided by 1 minus r. So let's just say I were to set this up for the problem that I see here. My first term is my a1, so a1 equals 1, and each time I am multiplying by 1/2, so that is my common ratio. So if I were to set this up, I would have 1 times 1 minus 1/2 to the nth power, and then all over 1 minus 1/2. All right, well, if I were to go ahead and just do some exploring here and type in 1/2 to the 10th power, or 1/2 to the 50th power, 1/2 to the 100th power, we're going to notice that these values keep on getting smaller and smaller each time. And so because of this, as I were to go to infinity, eventually this entire term right here, this 1/2 to the n, would become so small that it is essentially equal to 0. So in that case, I'm doing 1 minus 0, and 1 minus 0 is just 1, which means that this entire term is irrelevant. So what we can say is for an infinite series that is geometric with the absolute value of r being less than 1. In this case, we can say that the infinite sum is represented with the formula a1 over 1 minus r. So in this case, if I were to complete the problem using that formula, I would have 1 over 1 minus 1/2, which is essentially 1 over 1/2 or 2. So if I were to keep on adding these terms, 1 plus 1/2 plus 1/4 plus 1/8, and so on and so on and so on, that answer would get closer and closer to 2. Alrighty, let's go ahead and try a couple practice problems. So again, this up here is our formula that we are learning today. And notice that each of these says find the sum if it exists. So we first need to find that r value to see if in fact the absolute value of r is less than 1. Okay, so if we look at this first problem, a1 equals 24, and my r value, notice that I am alternating signs each time, which means that my r value is negative, and my r value is -1/3. Now, a quick refresher, one of the ways that we learned to define the r value is to divide consecutive terms. So if I was looking at this problem and I wasn't quite sure if it was geometric in nature, I could do -8 divided by 24, which gives me -1/3. And then I could try the next two terms and do 8/3 divided by -8, and I would get -1/3. And you can divide any two consecutive terms, so I always pick the easier two to work with. And for this problem, that would be the first two terms. All right, so now that we verified that the absolute value of r is less than 1, we can use our formula. So my infinite sum equals 24 divided by 1 minus r, so 1 minus negative 1/3. So 24 over 4/3 turns into 18. All right, now for example 2, in this problem we are looking at our formula written in summation notation. Now when we see that, remember that this right here is my formula for a sub n. So this is like saying a sub n equals 2 times 1/3 to the n minus 2. And like we talked about in class, the value that is being raised to the variable exponent is the r value. So r equals 1/3. Now, we've got to be careful because this number here, we want to assume that a sub 1 is 2. However, notice that this exponent says n minus 2. So I'm going to actually use the formula to calculate my first term. So my first term will be 2 times 1/3 the exponent of 1 minus 2. So 2 times 1/3 to the negative 1. Recall a negative exponent means that that fraction flips over. So you have 2 times 3, which is actually 6. That's why it's always important not to assume that that number in front of the r value is your a1. Okay, so now that we have a1 and we have r, we can go ahead and do our formula. 6 over 1 minus 1/3, 6 over 2/3, which gives us 9. All right. Go ahead and try these 3 problems on your own. Okay, sorry about that. All right, so when we look at these solutions, we'll notice when we look at example 3 that this is not a geometric series. This is in fact an arithmetic series. If you're not positive, find the first couple terms of the sequence, and then we can see that it does not follow the geometric model. We can also tell that here because we have a constant multiplied by a variable instead of a constant raised to a variable power. So number 3 does not exist. There is no sum. In example 4, we are geometric here. Our a1 is 3/4, the r is 2/3. This works for us, so we do our formula and we get 9/4. And for example 5, this is a geometric series. However, the r value is 9/8. And since r is greater than 1, this sum does not exist. So again, we can use the acronym DNE. All right, the other topic for today that we are going to look at is how to write repeating decimals as fractions. So we are going to break this up into 2 parts. First, we are going to go ahead and we are going to separate the repeating part of the decimal from non-repeating parts of a whole number. Then we will rewrite it as a sum of the finite, which means non-repeating and infinite fractions. We'll evaluate the sum and simplify our fraction. Okay, so if I were looking at this repeating decimal, this is essentially the number 0.515151 and so on. And I could also write this as 0.51 plus 0.0051 plus 0.000051 plus and so on. And as I add down, I would get the repeating decimal of 515151. Now, if I were to think of it that way, each of these decimals, the 0.51 and the 0.0051, each of these decimals can be written as 51 over a power of 10. And to figure out what power of 10 that we need, you want to look at how many places we have after the decimal point. So in the first one, since I have 2 places, that is the 100th place, I would write this as 51 over 100. So 2 decimal places means we need 2 zeros. Now for the next one, this would be 51 over, I have 4 places, so I'm going to write 4 zeros. This is actually my 10,000th place. And I can continue in this fashion. 1, 2, 3, 4, 5, 6 zeros necessary. Now you'll notice that each time the number of zeros that I have is increasing by 2. And so since I'm increasing by 2 zeros each time, that means that my r value is 1 over 100 because each time I am repeating 2 places. So I could think of this like my first term, A1, is 51 over 100. My R value, the way that I'm multiplying to go from term to term, is 1 over 100. And then now the infinite sum of all of these fractions will give me the fraction that represents this repeated decimal. So I can put all this together and say that this decimal, that's crazy, in its repeating form is going to equal A1, so 51 over 100 divided by 1 minus R, so 1 minus 100. Now I'm going to recommend that you leave all of this in terms of the same denominator. So even if 51 over 100 reduced, I would say leave it. So right now, I'm going to move this up here so I have more room. I have 51 over 100 over 100 over 100 minus 1 over 100. So that gives me 51 over 100 all over 99 over 100. And we've talked about this earlier in the year. When we have the exact same denominators, what's going to happen is those cancel. And I simply get 51 over 99. Now, here's the coolest part about this. Take your calculator out, do 51 divided by 99, and you will get this repeating decimal. So it's really easy to check your work. Okay, let's go ahead and try another one where we have repeating parts and non-repeating parts together. So in this case, my 0.6 is non-repeating, and my 7.5 is repeating. So if I were to write this as a sum of decimals, it would look like 0.6 plus 0.075 plus 0.00075, and so on. Now this step here is not necessary, but I find it helpful in the beginning to figure out what the fractions are, your initial term, and your R value. Now we can kind of think of this like 2 different pieces. The 0.6 doesn't match this model over here because it has nothing to do with the 7.5 that's repeating. So since this is a 1 place value, I would write this as 6 over 10. 1 place digit means I have 1 0 in my denominator. And then now when I go to do my repeating portion, this will be 75 over 3 places means I need 3 zeros in the denominator. And then here, 75, 1, 2, 3, 5 places means I need 5 zeros, and so on. Now this right here is my A1. And then if I look at how I changed from term to term, I had 3 zeros, now I have 5 zeros. So I increased by 2 zeros, so my R value is 1 over 100. You can also think about that because we have 2 places that are repeating. So if I had 1 digit repeating, my R is 1 over 10. If I have 2 digits repeating, my R is 1 over 100. 3 digits repeating, 1 over 1000, and so forth. Okay, so now I'm going to go ahead and do my infinite sum to get this part over here. So my infinite sum will be A1, 75 over 1000 over 1 minus R, 1 over 100. Okay, so if we go ahead and, sorry that is so obnoxious, if we go ahead and simplify this, whether we do on the calculator or by hand, we end up getting 5 over 66. And then now we put it all together by adding these 2 decimals and adding 6/10 plus 5 over 66, and we get the final answer of 223 over 330. All right, go ahead and try example 8 on your own, and when you're done, unpause the video and take a look at the work. Okay, so here what you can see is we went ahead and we wrote the 2 and the 4/10, which were the non-repeating parts by themselves, and that's what we see here in here. And then we can go ahead and we can take this later part here and represent it as an infinite sum. And then when we're all done, we add the fractions together. Depending on your calculator will determine on how much of this intermediate work, like I did here, that you need to do before you can go to the calculator. All right, that is it, and good luck. The nice thing about this is that you can practice any fractions you see. You can just write yourself a repeating decimal, and then go ahead and write it as a fraction and check your answer.